Hi, I'm an old guy and I do maths. And this is one of the most favorite things that I do in maths with my students. I absolutely love this demonstration because it really brings home the magic, in inverted commas, that is mathematics. When I say magic, I don't mean hocus pocus. I mean that what this shows is that there's an underlying mathematical relationship between things in this world. Let's have a look at this. So, what I've got here, I'll just explain this drawing. I've got a function here, y equals x plus 1, and I've graphed it on a Cartesian plane, and I've been unusually careful for me. I've drawn things with a ruler. So y equals x plus 1. This point here is 0, 1. So the point on the y-axis here is 1. That's important. And so I've drawn in this graph carefully. And what I've done then is I've drawn in a triangle with a side of 4 and a base of 4 here, because we've gone from 0 to 4 here, and if we put 4 into this function, the point that we get up here is 4, 5, which is 5 on the y-axis. So the distance between here is 5, and the distance between here and here is 4. The distance between here and here is 4, and the distance between here and here is 1. Okay, so what I then do is I work out the area that is enclosed by this line and the x and y axis. So it's composed of a triangle and a rectangle, and it's really easy to work out. The area of the triangle is 4 times 4 divided by 2. The area of this rectangle here is 4 times 1. So this works out to 12 square units, whatever those units are. Now, you have got to the point of watching this because you've already done differentiation, hopefully, and you're just getting introduced to integration and anti-differentiation. And what I'm about to do involves integration. And what does integration allow you to discover? Well, it allows you to discover the area between the x-axis and a curve. Now, it's possible that you've raised an objection in your mind that this is not a curve, it's a straight line. My response to that is the response that a teacher of mine had nearly half a century ago, in fact probably more than half a century ago, which is concerning. He told his class that a straight line was merely a curve without a bend in it. And that's pretty much how we view these things in mathematics. Just view this as a straight curve for the purposes of this demonstration. It's only for the purposes of demonstration because it's pretty easy to work out the area between a straight line and another straight line. What we really reserve, what I'm about to do for, is where we have curves, but this is an easy demonstration. Okay, so we know that this is 12 units square. Now, what I'm going to do is I'm going to take this function and I'm going to integrate it. I'm going to anti-differentiate it. Let's put it more precisely. Okay, so here goes. I hope you've been taught the basics of this, but I'll just go through this. We'll come to this in a minute. I'm just taking this function and I'm going to anti-differentiate it. Now, this is the essence of the function, x plus 1. And what I do is I say to myself, well, that is x to the power of 1, and this is 1x to the power of 0. And the process is that I add 1 to this number, and when I have done that, I also divide this by that number. So that gives me 1 plus 1 is 2, and I divide by that number. I add 1 to this, and I get 1 times x to the power of 1. Let's just do that. And I divide by 1. So that's really just x squared over 2 plus x. Now, when you've been taught how to anti-differentiate, you would have learnt that you put a value here, c, because you don't know what was here in most cases. Now, when we're dealing with what's called a definite integral, we don't do that. We're interested in these things here. And the notation for the creation of a definite integral looks like this. Now, the idea of a definite integral is that we're interested in points between something here and something here, which is replicated here. So we're looking for the value of the definite integral of x plus 1. So that's what this notation is, between the points 0 and 4. Now the general process is that you work out the value of this by putting this number into this function here. And you work out the value of this by doing the same. And then you subtract the value of this from the value of that. Now if you look at this, the value of the function with this in it is going to be 0. So all we need to do is this. That's what makes this a demonstration, and that's what makes it quick and easy to do. So if I put 4 into this, which I'm going to do back up here so that you can compare. So we've got, just keep an eye on where my finger is. We've got x squared over 2. Now x squared in this case will be 4 squared. So that is 4 squared over 2, please note, plus x, 4. 4 times 1, 4. And that equals 12 units squared. Isn't that fabulous? That is the wonder of mathematics. And that is hopefully an understandable and practical, well, maybe not practical, an understandable and impractical example of how definite integrals work. Thanks very much for watching. See you next time.